Bernhard Riemann's redefinition of space and geometry represents one of the most profound turning points in the entire history of mathematics. To appreciate how radical his contribution was, it is necessary to understand the intellectual environment in which he worked. For over 2,000 years, geometry was dominated by the ideas of Euclid. Euclidean geometry described space as flat, uniform, and governed by fixed rules such as parallel lines never meeting and the angles of a triangle always adding up to 180 degrees. These assumptions were not merely mathematical conveniences. They were widely believed to describe the actual structure of physical space itself. Geometry, in this classical sense, was seen as a mirror of reality. Riemann questioned this deeply ingrained belief. Instead of asking how geometry should look based on ancient axioms, he asked a far more fundamental question: what is space, really, and how do we measure it? This shift in perspective was revolutionary. Riemann proposed that geometry should not be restricted to flat surfaces or rigid rules inherited from tradition. Instead, geometry should be flexible enough to describe any kind of space, including spaces that are curved, distorted, or exist in higher dimensions beyond human intuition. In doing so, he transformed geometry from a fixed system into a dynamic and universal language. At the heart of Riemann's idea was the notion that space does not need to be flat. He imagined spaces where the usual rules of Euclidean geometry do not apply, such as surfaces where parallel lines can meet or diverge, and where the angles of a triangle can add up to more or less than 180 degrees. These ideas were not entirely new. Euclidean geometries had been explored by mathematicians like Gauss, Bolyai, and Lobachevsky, but Riemann took the concept much further. He provided a general framework that could describe all possible geometries in a unified way. Riemann introduced the concept of what are now called manifolds. A manifold is a space that may look complicated as a whole, but appears simple when examined locally. For example, the surface of the Earth is curved, but if you stand in one place and look around, it seems flat. Riemann realized that this idea could be generalized to spaces of any number of dimensions. A manifold does not need to exist physically. It can be an abstract mathematical object defined by certain properties. This insight allowed mathematicians to study spaces that could not be visualized, but could be rigorously analyzed. What truly distinguished Riemann's work was his method of defining geometry through measurement rather than assumption. Instead of starting with axioms about straight lines and angles, he began with the idea of distance. He asked how one could measure the length of a curve or the distance between nearby points in a general space. From this perspective, geometry becomes a study of how distances behave. Riemann formalized this idea by introducing what is now known as the Riemannian metric, a mathematical tool that specifies how distances and angles are measured at each point in a space. The Riemannian metric made it possible to calculate curvature, which describes how a space bends or deviates from flatness. Curvature is not just a visual concept, but a precise mathematical quantity. Riemann showed that curvature could vary from point to point, meaning that space itself could be uneven or distorted in complex ways. This was a dramatic departure from the classical view of space as uniform and unchanging. In Riemann's vision, space became something alive, something that could stretch, bend, and respond to internal structure. This new understanding of space had enormous consequences. In mathematics, it opened the door to entire fields such as differential geometry and topology. Mathematicians were no longer limited to studying shapes embedded in ordinary three-dimensional space. They could now explore abstract spaces that arise naturally in equations, functions, and physical theories. Concepts like geodesics, the shortest paths in curved spaces, generalized the idea of straight lines and became essential tools in both mathematics and physics. Perhaps the most dramatic confirmation of Riemann's ideas came decades later with the development of modern physics. Albert Einstein's theory of general relativity is built directly on Riemann's conception of geometry. Einstein proposed that gravity is not a force acting at a distance, but a result of the curvature of spacetime caused by mass and energy. To express this idea mathematically, Einstein relied on Riemannian geometry and its extensions. Without Riemann's redefinition of space, general relativity could not have been formulated. The way we understand black holes, gravitational waves, and the expansion of the universe all traces back to Riemann's original insights. Riemann's contribution also changed the philosophical understanding of mathematics. By showing that multiple geometries are possible, he demonstrated that mathematical truth is not necessarily tied to physical intuition. Geometry became a study of logical structures rather than a direct description of the physical world. This realization influenced later developments in mathematics, encouraging abstraction and the exploration of alternative systems. It also raised deep questions about the relationship between mathematics and reality, questions that continue to be debated today. What makes Riemann's achievement even more remarkable is the context in which it was presented. His famous ideas on geometry were introduced in a single lecture delivered in 1854, known as his habilitation lecture. In this lecture, Riemann did not provide extensive proofs or technical details. Instead, he offered a vision, a new way of thinking about space. That vision proved so powerful that generations of mathematicians expanded and formalized it, turning his insights into one of the central pillars of modern mathematics. In redefining space and geometry, Bernhard Riemann did more than solve a mathematical problem. He altered the framework within which problems could be posed and understood. Space was no longer a passive stage on which mathematics and physics played out. It became an active, variable structure that could be shaped by internal rules and relationships. This transformation continues to influence mathematics, physics, and philosophy, making Riemann's first keynote contribution a true turning point that changed mathematics forever. Bernhard Riemann's revolutionary approach to complex numbers and functions marked another decisive moment in the transformation of mathematics. Before Riemann, complex numbers were already known and used, especially in algebra and calculus, but they were often treated as strange, almost artificial tools. Many mathematicians accepted them because they worked, not because they were well understood. Functions involving complex numbers were powerful yet mysterious, full of paradoxes such as valued expressions and unexpected behaviors. Riemann brought clarity, unity, and deep geometric insight to this area, permanently changing how complex analysis is understood. To grasp the significance of Riemann's contribution, it is important to recognize the state of complex analysis in the early 19th century. Complex numbers, built from the square root of -1, had long been viewed with suspicion. While mathematicians like Euler and Cauchy had made great progress, much of the theory still relied on formal manipulation rather than intuitive understanding. Certain functions, such as the logarithm or complex roots, appeared to take multiple values, which seemed to violate the basic idea that a function should assign a single output to each input. This led to confusion and debates about rigor and meaning. Riemann's genius lay in realizing that these difficulties were not flaws in the functions themselves, but limitations in how mathematicians were viewing them. He introduced a geometric way of thinking that transformed complex analysis from a collection of technical tricks into a coherent theory. Instead of seeing complex numbers as pairs of real numbers or as algebraic symbols, Riemann emphasized their geometric nature. He viewed the complex plane as a space where functions act like mappings that transform one surface into another. This shift in perspective made it possible to understand complex functions in a far more natural and powerful way. One of Riemann's most important innovations was the concept of what are now called Riemann surfaces. These are geometric objects designed to make sense of multi-valued complex functions. For example, the complex square root has two possible values for each non-zero input. Rather than treating this as a problem, Riemann showed that the function becomes perfectly well-defined if it is viewed on a surface with multiple layers, carefully connected to each other. Each layer represents one branch of the function, and moving around certain points causes a transition from one layer to another. On this surface, the function behaves smoothly and consistently. This idea was revolutionary because it resolved long-standing paradoxes in a simple and elegant way. Instead of forcing functions to fit into an inappropriate framework, Riemann changed the framework itself. By doing so, he revealed that complexity and apparent contradictions often arise from an incomplete perspective rather than from the mathematics itself. Riemann surfaces allowed mathematicians to treat previously troublesome functions as natural objects, opening the door to deeper analysis and broader generalizations. Riemann also made fundamental contributions to the theory of analytic functions, which are complex functions that can be expressed as power series. He demonstrated that these functions are remarkably rigid. If they behave well in a small region, their behavior is tightly constrained everywhere else. This insight strengthened the connection between local properties and global structure, a theme that runs throughout Riemann's work. His ideas helped establish complex analysis as one of the most elegant and powerful branches of mathematics, known for its surprising results and deep internal unity. Another major aspect of Riemann's approach was his use of topology, the study of continuity and connectedness. Although topology did not yet exist as a formal discipline, Riemann intuitively understood its importance. He recognized that the global shape of a space affects how functions behave on it. Features such as holes, twists, and boundaries influence the existence and nature of complex functions. By linking analytic behavior to topological structure, Riemann laid the groundwork for future developments that would formally unite analysis, geometry, and topology. Riemann's work also brought a new level of rigor to complex analysis without sacrificing intuition. He balanced careful reasoning with geometric visualization, showing that precision and imagination could coexist. This approach influenced generations of mathematicians and helped shift the culture of mathematics toward greater conceptual clarity. Rather than focusing solely on computations, mathematicians were encouraged to seek underlying structures and unifying principles. The impact of Riemann's ideas on complex numbers and functions extends far beyond pure mathematics. Complex analysis plays a crucial role in physics, engineering, and applied sciences. Concepts developed by Riemann are used in fluid dynamics, electromagnetism, quantum mechanics, and signal processing. The ability to model waves, fields, and oscillations often depends on the properties of complex functions, first clarified by Riemann's work. Even modern technologies, such as electrical circuits and communication systems, rely indirectly on these foundational ideas. Perhaps most importantly, Riemann changed how mathematicians think about functions themselves. He showed that functions are not just formulas, but geometric objects with rich internal structure. This perspective encouraged the development of new fields, including algebraic geometry and modern topology, which continue to shape mathematical research today. His approach demonstrated that deep understanding often comes from viewing problems from multiple angles and being willing to redefine basic concepts. In the end, Bernhard Riemann's revolutionary approach to complex numbers and functions transformed confusion into clarity and fragmentation into unity. By introducing geometric insight, embracing abstraction, and resolving paradoxes through innovative frameworks, he elevated complex analysis to one of the central pillars of modern mathematics. This second keynote of his legacy stands as a testament to the power of reimagining fundamental ideas and shows how a single, profound shift in perspective can change mathematics forever. The Riemann hypothesis stands as one of the most profound and mysterious ideas ever proposed in mathematics, and it represents the third great keynote of Bernhard Riemann's lasting legacy. Unlike many mathematical contributions that are eventually completed, proven, and set aside, the Riemann hypothesis has remained unresolved for more than 160 years. Yet its power does not come from being unsolved alone. It comes from how deeply it connects the hidden order of numbers to the structure of mathematics itself. Through this single hypothesis, Riemann reshaped number theory and influenced vast areas of modern research. To understand why the Riemann hypothesis matters so deeply, one must begin with prime numbers. Primes are numbers greater than 1 that are divisible only by themselves and 1. They appear simple, yet their distribution among the natural numbers seems irregular and unpredictable. Mathematicians had long been fascinated by primes because they are the basic building blocks of arithmetic. Every whole number can be expressed as a product of primes, but no simple formula tells us exactly where the next prime will appear. For centuries, this apparent randomness posed one of mathematics' greatest challenges. Riemann approached this ancient problem from an entirely unexpected direction. Instead of studying primes directly, he examined a function defined using infinite sums and complex numbers, now known as the Riemann a function. At first glance, this function appears far removed from simple counting numbers. It involves raising integers to complex powers and adding infinitely many terms. However, Riemann discovered that this function encodes deep information about the distribution of prime numbers. This insight alone was revolutionary, revealing a hidden bridge between number theory and complex analysis. The key to this connection lies in the zeros of the a function, the values at which the function equals 0. Riemann found that these zeros are not random. They appear in specific regions of the complex plane. Some zeros are well understood and occur at negative even integers, but others, called non-trivial zeros, are far more mysterious. Riemann carefully studied their behavior and made a bold and precise conjecture. All non-trivial zeros of the a function, lie on a single vertical line in the complex plane. This statement, now known as the Riemann hypothesis, is simple to express yet astonishingly deep. What makes this hypothesis so powerful is its direct link to the distribution of prime numbers. If the hypothesis is true, it implies that primes are distributed as regularly as possible given their inherent unpredictability. It provides the strongest possible error bounds for how primes are spaced among the integers. In other words, the Riemann hypothesis offers a precise measure of how close reality comes to an ideal pattern. Even small improvements in understanding prime distribution have major consequences, and the Riemann hypothesis represents the ultimate refinement of this understanding. Since Riemann's time, mathematicians have verified that billions of non-trivial zeros do indeed lie on the predicted line, providing overwhelming numerical evidence in favor of the hypothesis. Yet no one has been able to produce a complete proof. This stubborn resistance has elevated the hypothesis to legendary status. It is not just an isolated problem, but a central organizing principle for modern number theory. Many theorems have been proven under the assumption that the Riemann hypothesis is true, showing how far reaching its consequences would be. The influence of the Riemann hypothesis extends far beyond number theory. It has deep connections to fields such as algebra, geometry, probability, and mathematical physics. Unexpected links have been discovered between the zeros of the zeta function and random matrix theory, a subject originally developed to model the behavior of atomic nuclei. These connections suggest that the same hidden structures govern phenomena across mathematics and physics, reinforcing the idea that the hypothesis touches something fundamentally universal. In practical terms, the Riemann hypothesis also affects modern technology. Prime numbers play a crucial role in cryptography, especially in systems that secure digital communication. While current encryption methods do not rely directly on the hypothesis, a deeper understanding of prime distribution could influence future algorithms and security models. This makes the problem not only theoretically important, but also relevant to the digital world. What is perhaps most remarkable is that Riemann himself devoted only a short paper to these ideas. In just a few pages, he outlined the zeta function, its connection to primes, and the hypothesis that now bears his name. He did not provide detailed proofs or extensive explanations. Instead, he offered a vision, trusting that future mathematicians would explore and expand upon it. This reflects Riemann's unique style, planting seeds rather than constructing finished monuments. The Riemann hypothesis has also shaped the culture of mathematics. It has inspired new methods, new fields, and new ways of thinking. Attempts to prove it have led to major advances, even though the final goal remains elusive. In this sense, the hypothesis has already been incredibly productive. It has acted as a guiding star, directing research and revealing unexpected connections across the mathematical landscape. Philosophically, the hypothesis raises deep questions about mathematical truth. Is it true simply because all evidence supports it, or does truth require a proof? Does its apparent inevitability reflect an underlying order in mathematics, or is it an illusion created by limited observation? These questions highlight how the Riemann hypothesis sits at the boundary between certainty and mystery, logic and intuition. In the end, the Riemann hypothesis represents more than an unsolved problem. It embodies Bernhard Riemann's ability to see hidden structures where others saw chaos. By linking prime numbers to complex analysis, he revealed a deep unity at the heart of mathematics. Whether the hypothesis is eventually proven or not, its influence has already changed mathematics forever. It stands as a testament to the power of bold ideas and the enduring impact of a single, brilliant insight. Bernhard Riemann's influence on modern science, physics, and technology forms the fourth and final keynote of how he changed mathematics forever. While many mathematicians leave their mark within the boundaries of pure theory, Riemann's ideas escaped those boundaries and reshaped humanity's understanding of the physical universe. His work demonstrates how abstract mathematical thought, developed without immediate practical goals, can later become essential for explaining reality and driving technological progress. One of the most profound ways Riemann influenced science is through his impact on physics, particularly in our understanding of space, time, and gravity. Before the 20th century, physics relied heavily on Euclidean geometry and Newtonian mechanics. Space was viewed as flat, absolute, and independent of the objects within it. Riemann's revolutionary ideas about curved spaces provided a completely new mathematical language, one that Albert Einstein would later use to construct the theory of general relativity. In this theory, gravity is no longer treated as a force acting between masses, but as the curvature of spacetime caused by mass and energy. This shift fundamentally altered how scientists describe the universe. Without Riemannian geometry, general relativity would not exist in its current form. Concepts such as geodesics, which generalize straight lines to curved spaces, describe how planets move around stars and how light bends near massive objects. These ideas are not abstract curiosities. They are essential for understanding black holes, gravitational waves, and the expansion of the universe. Every modern test of general relativity, from the bending of light during solar eclipses to the detection of gravitational waves, relies on mathematical structures first envisioned by Riemann. Riemann's influence also extends deeply into modern theoretical physics beyond gravity. Fields such as quantum field theory and string theory use advanced geometric and analytical tools rooted in Riemann's work. In these theories, the properties of particles and forces are often described using complex manifolds and curved spaces. Even when physicists explore dimensions beyond the familiar 3 of space and 1 of time, they rely on mathematical frameworks that trace back to Riemann's original ideas. In this sense, Riemann provided the vocabulary through which modern physics speaks. Beyond fundamental physics, Riemann's legacy is woven into many areas of applied science and technology. Complex analysis, which he helped shape, plays a crucial role in engineering disciplines. Electrical engineering, for example, uses complex functions to analyze alternating current circuits, signal behavior, and electromagnetic waves. The mathematical techniques that allow engineers to simplify and solve these problems are built on foundations laid by Riemann and his contemporaries. In fluid dynamics and aerodynamics, Riemann's ideas help model how fluids flow around objects. Conformal mappings, a concept refined through Riemann's work, allow engineers and scientists to transform complex flow patterns into simpler ones that can be analyzed more easily. This has practical applications in designing aircraft wings, predicting weather patterns, and understanding ocean currents. Although Riemann did not envision these applications, his abstract theories made them possible. Riemann's influence is also felt in modern computing and information technology. Number theory, deeply affected by the Riemann hypothesis and related ideas, underpins cryptography, which secures digital communication. While cryptographic systems do not depend directly on Riemann's results, the broader understanding of prime numbers and complex functions shaped by his work forms the intellectual background of modern encryption. In an age where data security is critical, Riemann's legacy quietly protects information across the globe. In data science and signal processing, techniques based on Fourier analysis and complex functions are essential for handling images, audio, and communication signals. These methods rely on mathematical principles that were clarified and expanded through Riemann's approach to analysis. From medical imaging technologies such as MRI scans to everyday tools like mobile phones and internet streaming, Riemann's mathematical influence is embedded in systems people use daily, often without realizing it. Riemann's impact is not limited to specific applications. It also shaped the way scientists think. His work encouraged the use of abstract models to describe reality, even when those models seem far removed from direct experience. This mindset has become central to modern science, where unseen structures and higher dimensional spaces are routinely invoked to explain observable phenomena. Riemann showed that abstraction is not an escape from reality, but a powerful way to understand it more deeply. Educationally, Riemann's ideas have transformed how mathematics and physics are taught at advanced levels. Courses in differential geometry, complex analysis, and mathematical physics all bear his imprint. Students learn to think in terms of structures, spaces, and transformations rather than just formulas. This way of thinking prepares scientists and engineers to tackle complex problems across disciplines, reinforcing Riemann's long-term influence on scientific culture. Perhaps the most remarkable aspect of Riemann's legacy is how seamlessly his ideas connect pure thought with practical impact. He worked in relative isolation, motivated by curiosity rather than application. Yet his insights proved so fundamental that they became indispensable tools for understanding nature and building technology. This demonstrates a powerful truth about mathematics. Ideas developed for their own sake can eventually reshape the world. In conclusion, Bernhard Riemann's influence on modern science, physics, and technology completes the picture of how he changed mathematics forever. By providing new ways to describe space, analyze functions, and understand structure, he enabled breakthroughs that continue to define our era. From the curvature of spacetime to the flow of information through digital networks, Riemann's ideas are everywhere. His legacy stands as a lasting reminder that deep, abstract thinking can illuminate the universe and transform human progress in ways no one could have predicted.